So one last sample problem here that actually has us calculating Kc, so kind of a type 1 type problem. The rest of the problems are kind of more typical where you're given a reaction, you're given an equilibrium constant, and you're asked to figure out, well, how much do you have when you actually get to equilibrium? Okay, this problem tells us in order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.2 moles of HI gas and allows the reaction to proceed at 453 degrees C. They tell us at equilibrium what the concentration of HI is, and they want us to calculate Kc. So again, if we start with the same systematic method with all of these problems, it's going to guarantee that you're going to get some partial credit for these problems, and hopefully it will allow you to navigate better how you need to solve the problem. So step 1 is always write the balanced chemical equation. Step 2 is write the reaction quotient. In this case, we're dealing with concentration, so we're going to write QC, and it's equal to H2 times I2 over HI squared. Third step is to always make sure we have the concentrations of our species in the right units. Since we're talking about C, we need to have molarity. So in this case, they tell us that we've got 0.2 moles of HI gas, so 0.200 moles of HI, and we know that it's in a 2-liter flask. And so that tells us that we have a 0.100 molar. And remember, this is equal to the HI concentration initially. Okay, we fill an evacuated flask, so this is the initial amount. They do give us HI at equilibrium as 0.078 molar, but if we want to calculate Kc, Kc equals the concentration of H2 at equilibrium times the concentration of I2 at equilibrium, or the concentration of HI at equilibrium. We're only given one of those pieces. This is a piece that we're given. We don't know these guys. If you don't know more than one equilibrium concentration, you probably need to use an ICE table. So let's go ahead and set up our ICE table, which kind of starts step 4. Step 1, equation. Step 2, reaction quotient. Step 3, make sure species are in the right units. Step 4 is to set up your ICE table. So ICE. They tell me that I have 0.100 molar. That's what we calculated HI. None of my other reactants. Because I have none of my other reactants, I know the only thing that I can do with this reaction, the only way that it can shift, is to have some of this go away. I use my stoichiometry for my reaction to give me a coefficient for my variable. And so my equilibrium concentrations are 0.100 minus 2x, x, and x. So again, this represents the equilibrium concentration of HI, the equilibrium concentration of H2, and the equilibrium concentration of I2. I need to know what all of these species are in order to put them into here, because this problem asks me to calculate Kc. Well, the good news is since they gave me one piece, I can set this one equal to 0.078. So I can say 0.078 equals the equilibrium concentration of HI equals 0.100 minus 2x. So this will allow me to solve for x. It allows me to solve for x and get that equal to 0.011 molar. And the nice thing is that directly equals my concentration of H2 at equilibrium and I2 at equilibrium. So carrying this down now, Kc is going to be equal to 0.011, 0.011, 0.078 squared. So Kc for this reaction at this temperature is 0.020. So this kind of problem is one where I'd say we can solve for x. So I'm going to kind of highlight for each of these. The method to solve for x is you are given one equilibrium concentration. So if you're given one equilibrium concentration, you can use that number to set equal to whatever your equilibrium expression was that had your variable, solve for your variable, and then substitute that variable back in for your other species.